box beam. Okay, so you can see down here. So for box beam, we have what? We have a point of initiation. We go for left, and there's a Q from the left and on the right. So that we have a Q on the left, on the right. So therefore, you have to consider what? You have to consider it to be what? 2Q. And because box beam, the area of analysis, you have to cover this area. Okay, you have to cover that area. So we're going to find the Q for point B, right? So the formula is still the same. The shear at point B is equal to V over I Q at point B, not theta. Q at point B divided by thickness. So with this, we know that thickness, right, is equal to 0.2 inches. Right? Why 0.2 inches? Because the thickness is perpendicular to the shear flow direction for thin wall analysis. Okay, so point B. So I'm going to put down here thin wall analysis. Okay, so we want to find the Q of point B. Okay, so the cube of point B again, width multiplied by depth multiplied by y bar. So the width that we are looking at is the width is 2 minus 0.3 minus 0.3. Then the depth is 0.2. And then the y bar is equal to 1.5. Why 1.5? Because this entire thickness is 3. So 1.5 minus by the centroid at the flange. So it's 0.2 divided by 2. Okay. So this will give us 2 minus 0.3 minus 0.3 times 0.2 times by 1.5 times by 1.5 minus 0.1. So it's equal to 0.392 inches cube. Okay, so 1.5. So from here, we know everything now. So we look at the shear at point B. So V and I, we're not worried yet. Why we are not worried about V and I? Because they are constant at point A, B, and tau max. Okay, so once we are able to identify the position, okay, so we have to identify the position of tau max. We can substitute where tau max is equal to what? 10 times 10 to the power 3. Then we know our V over I ratio. Okay, so for now, we don't need to worry about it. So V and over I is constant. So the Q is 0.392. The thickness is equal to 0.2. Right? Now, over here, you have to put a 2 down here because it's a what? You have what? 2Q. Why 2Q? Because on the box beam, you have 2Q going one towards the left, one towards the right, and the 2 is because of the 2Q. Okay, so you have to, that's why once you start analysis, you realize a box beam, you need to ensure that you put a 2Q up there, then you won't miss out. Okay, so 0.392 divided by 2 divided by 2 is 0.98 VI. Okay. Any questions so far? Anyone, please? Anyone? Are we okay? Right. So if that's the case, we are going to do another set. Okay. I'm going to copy the whole thing. Now we are going to find, okay, we're going to find the shear stress ratio at point A. Okay, so at point A, now I cover here. Okay, I cover the top. Okay, I cover the top. Okay, I got rid. I will get rid of this. Okay. So that's point A now. Okay, and I'm going to draw the shear flow direction. Right, and we're going to focus at point A now. Okay, we're going to focus at point A. So point A, this is my area. Given that what I've drawn down there, okay, so what I've drawn down there, so given what I've drawn down there, that stress at point A, right? So if you look at the analysis now, the analysis become what? Becomes a white flange. Right? So if you look at our white flange consideration, okay, so white flange, you only have going to alpha, you have an initiated point, okay, and it only covers the area. You only have one Q, okay, like for this case, you call it Q2 and Q1. Okay? You don't have two Qs at all, okay. So for this case, the Q is only Q. The Q is only, you only consider one Q, okay, you don't consider what? Two Q. Okay, so white flange, so this is a white flange thin wall. You only consider one Q. Okay. So from here, by applying to the rule that we have stated, that the datum is from where? Is from the centroid. The analysis will start where y is at the what? Y is at the maximum. So that's why you only consider this area. Okay, and the end of the point, the end of the shear flow is over there. Okay, so you only need to consider what? You only need to consider one arrow, and you only need to consider that area over there. You don't need to consider left and right there, left and right. Why? Because the shear flow over here. Okay, so your Q1 over here, I call it Q1. Your Q1 over here and your Q2 on the right hand side. For now, they are not initiating at the same point, so you only consider one side, or they don't end at the same point, so you only consider one side. Okay, you know what? It's not just initiated; it's where it ends also. Okay, so it end at only one point, one arrow. You only consider one Q. Q1 and Q2, they don't end at the same point. That's why you only consider one Q. Okay. So for now, what we have now, so your again, the shear at point A is equal to VQ over IT. So we know T over here, the perpendicular distance from the shear flow where the T is measured is again 0.2 inches. Okay, so the first moment of area at point A is equal to width multiplied by depth multiplied by y bar. So the width is equal to 0.7. The depth is equal to 0.2. The y bar again is 1.5 minus by 0.2 divided by 2. So over here you get 0.7, 0.2 minus, so it's 0.196. Inches to the power 3. Okay, so your shear at point A will be equal to V over I. QA is 0.196. Then we divide the whole thing by 2. So this is equal to 0.196. So 0.098 V over I. Okay, so from what we had before, our shear at point B is also equal to what? Our shear at point B is equal to shear at point A, 0.98. Okay, 0.98 VOI. I think I wrote wrongly, 0.98. I wonder why I put 0.9. Let's see, bye-bye. It's not 2, it's 0.2, sorry. Okay, it's 0.2 over here. Sorry, it's not 2.
1.043.
0.98. Okay. Someone say something. You get what again? We okay? We good? Okay.
I'm not getting that answer.
Which one? You're not getting the answer. 0.98?
0.196 divided by 0.2.
So 0.7
0.7 times
multiplied
0.2.
by 2 times by 1.5 minus 0.1. You have to open bracket, close bracket. 0.196. Right? Over here.
I get 0.2086. I don't know. Maybe I'm doing something wrong here.
So if you press 1.5 minus 0.1, then you multiply by 0.2, multiply by 7, you get 0.196. Right? Do you get it now, or we are still working on it? You okay? I don't hear you, so I'm going to carry on, okay? Right. So the next thing, let me know if you got it, okay? Or if you don't get it, our did the rest of you get 0.196? Or don't worry about that, okay? So I will do it again, okay?
Sorry, I had an extra 0 somewhere.
Okay, so we are okay, right? Good. Thank you for it. So now, the next point I'm going to declare a point down here, and this is my point C. Okay, I'm going to find my point C. Why I decided to find my point C? Because at point A, I get 0.98 V over I. At point B, I also get 0.98 V over I. So both are the same value. I can't say whether it's the maximum. So I'm going to check point C. Okay, we're going to check point C. And why we check at point C? Because at point C, right, Q at point C is going to be Q what? As a maximum. Okay. So I'm going to start from the top. Okay, we're going to start from the top for this case. So if I start from the top, what I see over here is we have a box beam. Analysis. And Q is going to be 2Q. Okay, so you have a shear force coming down from the vertical. You got Q going to one side, Q going to the other side, and then it will flow. It will flow. That's why you got one Q here, one Q here. That's why you have to consider what? 2Q. Okay. Next, we're going to find the first moment of area. So this is from the top. All right, from the top. So the first moment of area, Q, for point C is equal to what we have calculated. So the one we have calculated before is what? Where we have the flange is 0.392,